Okay, let's continue our discussion. We are on vertical stress caused by a rectangular loaded area. So if you're going to take the vertical stress at a certain point caused by a rectangular loaded area, so this is the vertical stress that you're going to take, and this is due to the rectangular loaded area. So the formula to that is stress is equal to, the vertical stress equal to Q times I sub 3. I sub 3 is given by this equation. And of course, you have the presence of M and N, which is M is Z all over Z, and N is equal to L all over Z. And you have here the variation of I sub 3. You just have to get the value of M and N, then identify what is the value for M and N, and identify your I sub 3 along the Y direction. So this is also a table showing the variations of I sub 3 having the value of M and N. So this one is the stress below an arbitrary point below a rectangularly loaded flexible area. So if you're going to take, or you're going to get the stress at any point below a rectangularly loaded area, so this, basically you have to divide that into 4 quadrants. So at this point, if you're going to observe, you have here 3 I sub 3, so you simply have to get the sum. Once you get the value for I sub 3 for quadrant 1, I sub 3 for this portion, I sub 3 for that portion, and I sub 3 for this portion, you multiply that one by Q, and you have now the stress increase at any point below a rectangular loaded area. And in most cases, the vertical stress increase below the center of a rectangular loaded area is given by this equation. So if you're going to get the stress below the center, this is the center of our rectangular area, below that one, you get the stress, you are given with this equation, Q is equal to I sub 4, wherein our I sub 4 is given by this equation. You have M1 and M2, and your small letter d. Our M1 and M2 is L over D and Z all over D, and our small letter d is given by the width all over 2. And we have a table for the value for I sub 4. We just need the value for our L over D and Z all over D. So we have the variations of I sub 4. We need the value for M1 and M1 and N1. This one is a figure showing the variations of I sub 4. You just have to get the value of L all over D and Z all over D so that you can get the value of I sub 4 on the y-axis. So we have here a sample problem. The plan of a uniformly loaded rectangular area is shown in the figure. Determine the vertical stress increase below 0.8 prime at a depth of Z is equal to 4. So this is our uniformly loaded rectangular area. So we're going to get the stress at 0.8 prime having a depth of 4 meters. So to get the stress at 0.8 prime due to this plan of a uniformly loaded rectangular area, we simply have to illustrate that in this manner. So we need to say, for this plan, we have to extend our, this one, the area of this extend up to 0.8 prime. So you have now 4 meters and 2 meters, of course. You have extended this one, and it should be subtracted. Whatever you have added should be subtracted. So that would be, you have to subtract your Q having a width of 1 meter. So you're going to have the solution. So you can have vertical stress to be equal to the stress at this point subtracted by the stress at this point. So of course your Q here is equivalent to 150 kN per meter squared. This is also 150 kN per meter squared. And your stress sigma sub 1 is due to the loaded area as shown in this figure, and your stress sigma sub 2 is the loaded area, the stress due to the loaded area in this figure. And we have to compute for M and N, so basically that is 0.5 for M and N is equal to 1. And from figure 10.6, having m is equal to 0.5 and n is equal to 1, we can get our I sub 3, which is 0.1225. So you multiply your I sub 3 to q so that we can have our stress, and it gives us our stress, which is 18.38 kilonewton per meter squared. So basically, from the third figure, the last figure, the figure wherein you're going to subtract, you have to identify your m and n. So this is the figure that we're talking about, that's one. So get the m and n for that, and n is 0.25 and n is equal to 0.5. And using your figure 10.26, you can get your I sub 3, which is 0.0473. And multiply this 1 to 150, which is our q. It gives us 7.1 kilonewton per meter squared. Then you subtract your 18.38 minus 7.1. So now this vertical stress caused by this uniformly loaded area is equal to 11.28 kilonewton per meter squared. So basically that ends our discussion for stress distribution. So in the stress distribution, we need to say the stress that the stress at a certain point due to a certain load applied in a certain specific area. Thank you.